probability tree. It is a method to calculate the probability of events with repeated trials with or without replacements. The probability tree, it is a tree lying down with a trunk and branches. This other branch further divides into two other branches. This other one further divides into two other branches. This division continues. This one can further divide into two other branches, two branches, two branches, and so on. This is the trunk. This is a branch. This is another branch. These are other ones. Events are always written at the end of the branches. Let's say here I have an event A, and here I have an event B, and let's say here I have an event C, I have an event D, and here I have an event E, I have an event F. On the branch, they always write probability of event A, and here is probability of event B. On this branch, write probability of event E. Here I write probability of event F. On this branch is probability of C, and here I have probability of event D. I can write outside the branch or inside the branch is okay. If you look carefully, this is the first set of branch, which are 2. The second set of branch are 4. And if these branches split to other branches, we'll have the third set of branches, which will be 8 branches. And then we'll continue to 16 branches and so on. This first set of branches is called first trial. The second set of branches is called the second trial. The third set of branches is called the third trial, and the other fourth trial. You have to take note that this probability here of C depends on the probability of A. So it depends on the branch before it. So actually they call this probability of C, but it means probability of C given that A has occurred. It also means probability of if A then C. So that is probability of C, which is the second branch from here. It means probability of C given that A has occurred. It also means probability of if A has occurred, then C is the same here in this branch. Probability of V means probability of D given that A has occurred, or probability of if A then D. The same here. Probability of E means probability of E given that B has occurred, or probability of if B then E, and so on. You see, if we follow from the beginning up to here, we can call this branch 1. Now if we follow like this, we can also call this branch 2. And if we follow from the beginning, we go like this, we can also call this branch 3. Follow here, you can call this branch 4. You have to know that along a branch, from the starting to the end, we talk about an or intersection of events. So it means along this line, we have probability of A intersection C. The same along this branch is probability of A intersection D. Along this branch is probability of B intersection E. Along this one, we have probability of B intersection F. And probabilities along a branch are always independent. That means the probability along the branch 1 is equals to probability of A intersection C, which is the same like probability of A times probability of B. Along the second branch, that is probability of branch 2 is equals to probability of A intersection D. Since there is independence along a branch, so we have probability of A times probability of D, and so on. Here is probability of B times probability of E. Along this branch, we have probability of B times probability of F. You also have to know that from one branch to another, we talk of or union. That is, to combine branch 1 and branch 2, we talk of OR. That is, probability of branch 1 union branch 2 is equals to probability of branch 1 plus probability of branch 2. So you have to know that probabilities from one branch to another are mutually exclusive. Mutually exclusive means probability of branch 1 intersection branch 2 is equals to 0. So that is why I'm having only probability of branch 1 plus probability of branch 2. I can still combine all the 4 branches. That is probability of branch 1 union branch 2 union branch 3 union branch 4 is equals to probability of branch 1 plus probability of branch 2 plus probability of branch 3 plus probability of branch 4. Since the probabilities from one branch to the other are always mutually exclusive. Take note that when we are moving along the branch, we talk of the AND or intersection of events. And the probability of the intersection of these events are always independent. And also take note that when we are moving from a branch to another, or when we want to combine two or more branches, we talk of OR or union, and this combination is always mutually exclusive. That is, the probability of the intersection of the events are always 0. Let's do an example to apply the idea of the probability tree. A bag contains 4 red balls and 3 blue balls. A trial consists in drawing a ball at random, noting its color and keeping it outside. 2 trials are made. A. Draw a probability tree diagram for the experiment. So in this question, they said 2 trials were made. It means there is the first trial and there is the second trial. You need to first start by attributing letters to the events involved. The events are drawing a red and drawing a blue ball in the first and the second trial. So I can say, okay, let R1, R2 be the events of drawing a red ball in the first and the second trial, and B1, B2 be the events of drawing a blue ball in the first and the second trial. So there were 2 trials, means my probability tree, we have the first trial, which is always made of 2 branches, and then I had a red ball in the first trial and I had a blue ball in the first trial, and the second trial will be made of 4 branches, 2 branches here, 2 branches here. And then in the second trial I had R2, that is the second red ball, and I had the second blue ball. Here I had the second red ball, here I had the second blue ball. So I need to write the probability of drawing the first red ball. You know, the total number of balls, which is n of s, is equals to 4 plus 3, which is equals to 7. S stands for the sample space. That is, total number of elements in the sample space is equals to 4 plus 3, which is 7. And the probability of red balls is equals to the number of red balls all over the number of elements in the sample space, which is the total number of balls. You know, this is from the formula of probability, which is equals to 4 red balls all over 7. That's the probability of drawing a red ball is 4 over 7. And the probability of drawing a blue ball is equals to number of blue balls all over number in the sample space, which is equals to 3 on 7. So here is 3 on 7. You know, this trial consists in drawing a ball at random, noting its color and keeping it outside. So in the first trial, a red ball was taken out of the bag and then it was not replaced back. That's, it was kept outside. So if the red ball was kept outside of the bag, it means that the number of red balls remaining in the bag in the second trial will be 3. What I'm trying to say that if you remove the first ball in the first trial, it means going for the second time to remove a red ball, the total number of red balls remaining will be 3, not 4 again. And the total number of balls that will be in the bag will not be 7 again, but will instead be 6. So it means the probability of obtaining a red ball in the second trial will be 3 on 6. You got to know that the sum of probability at a branch is always 1. If you look carefully here, you see that 4 over 7 plus 3 over 7 is equals to 7 over 7. That's the same SCM here had 4 plus 7, 7 over 7, which is 1. That is always the case with a tree diagram. So the sum of probability at a branch is always 1. The same here, the sum of probability in this branch is supposed to be 1. So to obtain the probability of the blue ball in the second trial, I need not to reason again. I just have to take 1 minus 3 on 6, which is the same like 6 times 1 minus 3 on 6. That's 6 times 1 is 6. 6 minus 3 is 3. 3 on 6. So here the probability of drawing a blue ball, the second trial, is 3 on 6. Now if in the first trial I removed a blue ball from the bag, when I want to go the second time to remove a blue ball, there will not be 3 blue balls again. There will be remaining 2 blue balls in the bag. Since the condition was that when I remove a ball, I don't bring it back again, I keep it outside. That was the condition. So if I remove a blue ball in the first trial and I kept outside, going for the second time, there will be 2 blue balls remaining, not 3. And that means the total number of balls remaining will be instead 6. So it means the probability of a blue ball in the second trial will be 2 on 6 here. That is in the condition that I remove a blue ball in the first trial, so I'll have 2 on 6. And if I have 2 on 6 here, it means to get the other probability in the other branch, I just take 1 minus 2 on 6, which is the same like 6 times 1 minus 2 on 6, which is 6 minus 2, 4 on 6. Since the sum of probability at the branch is always 1, so it means here I have 4 on 6. So this is the probability tree diagram that was required. Now find the probability that B, a ball of either color, is drawn as B. That's probability of a ball of either color. Probability of a ball of either color means that the 2 balls I will draw from the bag in the first and the second trial can either be red and blue ball or blue and red ball. That means in the first trial I can go, maybe I had a red ball, and then in the second trial I had a blue ball. Or here, or means plus or union, so that's it, plus. Or in the first trial I had a blue ball, and in the second trial I had a red ball. And you know that probability of red ball in first trial intersection blue ball in second trial is the same like probability of red ball times probability of blue ball. So in the first trial, the probability of the red ball is 4 on 7, and the probability of blue ball is 3 on 6. No, probabilities along a branch are independent, so that is why I multiply 3 on 6 plus probability of blue ball in the first trial, which is 3 on 7, times probability of red ball in the second trial is 4 on 6. And then it's the same like 4 times 3 is 12 all over 7 times 6, which is 42, plus 12 on 42. When I add this, I'll have 24 on 42, which is the same like 4 on 7. That is 6 here is 4 times, 6 here is 7 times. That means probability of either color is 4 on 7. Another easy way to bring out this formula is to look at the branch where the colors are not the same. If you look at the probability tree here, you discover that along this branch, the colors are not the same. Thus, we have red in the first trial and blue in the second trial. But along this branch, the colors are the same, so we don't need the branch. And then we look again here. Along this branch, the colors are not the same. That's blue and then red. So we need the branch. But if we follow this branch, we don't need it because the colors are the same, blue and blue. So with that, we know along a branch, we are talking of intersection of events. That's we're talking of probability of R1 intersection R2. And then when we are moving from one branch to the other, we're talking of addition or. That is, or probability of B1 intersection R2. So, and then it gives this formula. So that is the fastest way to bring out the formula. C part, find the probability of both balls are of the same color. That's C, probability of both balls of same color is equals to probability of red and the red, or probability of blue and blue. That is, probability of both balls of same color means the 2 balls are of the same color. Now to get this formula, you come to the tree diagram, you look for the branch in which the 2 balls are of the same color. Now if we look at this branch, you see that in the first trial we had red and in the second trial we had red. But we cannot take this branch because it's red and blue, so we are looking for same color. Now if we come to this branch, we see that along this branch here we had blue and blue, so we don't need this branch because it is blue and red, so we need same color, blue and blue. So along the branch we're talking of intersection. That is the formula, that's intersection of events, and these intersection of events are independent. So here I had probability of R1 intersection R2, and then from a branch to another we're talking of union or, and this or here is mutually exclusive, so that's what we're talking of, plus probability of B1 intersection B2. And you know that probability of R1 intersection R2, they are independent, so we have probability of R1 times probability of R2 plus probability of B1 times probability of B2, and then probability of R1 is 4 on 7 times probability of R2, which is 3 on 6, plus probability of B1, which is 3 on 7 times probability of B2, which is 2 on 6. From here you see 4 times 3 is 12 on 42 plus 6 on 42, which is equals to 12 plus 6, 18 on 42. And you see 6 can go to 18 3 times, 6 can go to 42 7 times, which is the same like 3 on 7. Exactly 2 red balls are drawn. That's the probability of exactly 2 red balls is equals to the probability of R1 intersection R2. Along a branch we are talking about intersection, and the branch in which we have only 2 red balls is this one, that is in the first and the second trial. So along a branch we talk of intersection, that's why I'm having probability of R1 intersection R2. And along a branch the events are independent, that means probability of R1 intersection R2 is the same like probability of R1 times probability of R2, and probability of R1 along that branch is 4 on 7 times 3 on 6, which is equals to 4 times 3 is 12 on 42, which is the same like 2 on 7. That 6 goes here 2 times, 6 go to 42 7 times. This is another example. A and B are 2 events such that probability of A is equals to 2 on 5, probability of B prime given A is equals to 3 on 4, and probability of B given A prime is equals to 1 on 3. A. Draw a fully labeled tree diagram with A preceding B. A preceding B means in the first trial what we should have is event A only. That is, if we are having only event A, it means this will be A prime, and in the second trial it has 4 branches, we should have only event B. That means here I had B and then B prime, and here I have B prime. This is the meaning of A preceding B. That is, preceding means A first then B second, and the probability of A given is 2 on 5. That means the probability of A prime will be 1 minus probability of A from the formula of complementary events. That is, probability of A prime is always equals to 1 minus probability of A. That is 1 minus 2 on 5, which is the same like 5 times 1 is 5 minus 2 is 3, so 3 on 5. So it means probability of A prime is 3 on 5. Probability of B is not given. Remember earlier we said that probability of an event in the next trial is always depending on the preceding trial. So that means probability of B prime here is also means probability of B prime given that A has occurred. That is the meaning here. So if that's the meaning, it means that probability of B prime here is the same like 3 on 4 from the equation. That is 3 on 4. So it means that here is 3 on 4. And if here is 3 on 4, the sum of probability at the branch is always 1. That means the probability here is 1 minus 3 on 4, which is equals to 1 over 4. That's 4 times 1, which is 4 minus 3 is 1 on 4. So it means here is 1 on 4. And here, probability of B prime here depends on probability of A prime, and probability of B here depends on probability of A prime. So it means the probability of B here, that's along this branch, is the same like probability of B is equals to probability of B given that A prime has occurred. So it means that probability of B here is the same like 1 on 3 as given in the equation. So it means here is 1 on 3, and if here is 1 on 3, it means that here will be 1 minus 1 on 3, since the sum of probability at the branch is 1. So it means probability of B prime here, which also depends on A prime, is the same like 1 minus 1 on 3, which is 3 minus 1 on 3, which is equals to 2 on 3. So here I have 2 on 3. So this is the tree diagram. Now B, calculate Roman 1 probability of A intersection B. That's probability of A intersection B. Probability of A intersection B is the same like probability of A times probability of B. Since the probability of events along a branch are always an intersection and are always independent, so we have 2 on 5 times 1 on 4, which is the same like 2 here 1, 2 here 2 times. That's 1 on 10, since 5 times 2 is 10. So it means here is 1 on 10. Now Roman 2, probability of A prime intersection B should be equals to probability of A prime times probability of B. Since A prime and B are along this branch, so they must be independent. So that is, we have 3 on 5 times 1 on 3, which is the same like 1 on 5. Since 3 cancel here 1 time, 3 1, so we have 1 times 1 is 1, and then 1 times 5 5. As here is 1 on 5. Roman 3, probability of B. From complementary events, probability of B is obtained by the formula probability of B intersection A plus probability of B intersection A prime. Sometimes you can be wondering why here this probability of B and then probability of B here, and why calculating probability of B again. I still recall you that probability of B here is the probability of B depending on A. That's given that A has occurred. It is not the probability of B. It is the probability of B depending on A. And here is another probability of B depending on A prime. So we need to get the probability of B itself depending on none of these, which is obtained by this formula. So that is probability of B intersection A. We obtain it from Roman 1 as 1 on 10 plus probability of B intersection A prime, which we obtained as 1 on 5. A prime intersection B is the same like B intersection A prime. That is, probability of A prime intersection B is the same like probability of B intersection A prime. So probability of B intersection A prime here is the same like probability of A prime intersection B. So that is why I am writing 1 on 5 here. Let's say I look for the LCM. I'll have 10 here 1, 1 times 1 is 1, 5 here 2, 2 times 1 is 2, which is the same like 1 plus 2 is 3 on 10. So it means probability of B here is equals to 3 on 10. Roman 4, probability of A union B. By definition, probability of A union B is equals to probability of A plus probability of B minus probability of A intersection B. Probability of A is given as 2 on 5 plus probability of B, which is 3 on 10, that is 3 on 10, minus probability of A intersection B, which we obtain as 1 on 10. Now here we can look for the LCM. 10, 5 goes to 10, 2 times 2 is 4, plus 10 goes to 10 1 time, 1 times 3 is 3, minus 10 divides 10, 1 times 1 is 1, which is equals to 4 plus 3, 7 minus 1 is 6 on 10, which is the same like 3 on 5. That's 2 goes here 3 times, 2 goes here 5 times. That means probability of A union B is 3 on 5. Roman 5, probability of A given B is given by the formula probability of A intersection B all over probability of B. Probability of A intersection B is this, which is 1 on 10 all over probability of B, which is this, that is 3 on 10. That's dividing two fractions. We invert the fraction at the denominator times the one at the numerator. So here I have 1 on 10 times 10 on 3. Since you invert 3 on 10, you have 10 on 3. And see 10 here, cancel 10 here. So we'll be left with 1 on 3. That is 1 times 1 is 1, 3 times 1 is 3. So it means this is 1 on 3. Now got Romans 6. Probability of A prime given B prime. Probability of A prime given B prime is given by the formula probability of A prime intersection B prime all over probability of B prime. From the tree diagram, probability of A prime intersection B prime is the same like probability of A prime times probability of B prime. That is, if we are following this branch here, that is all over probability of B prime, which is the same like 1 minus probability of B. Probability of A prime along this branch is 3 on 5 times probability of B prime along that branch, which is 2 on 3 all over 1 minus probability of B, which we obtain as 3 on 10. That is 1 minus 3 on 10. 3 on 5 times 2 on 3 is the same like 2 on 5. Since 3 cancel here 1, 3 cancel 1, so we have 2 on 5. And the 1 minus 3 on 10 is the same like 10 minus 3 on 10, which is 7 on 10. Now if we invert these two fractions and multiply, we'll have 2 on 5 times 10 on 7. And you see 5 here 1, 5 here 2 times 2 times 2 is 4, which is 4 on 7. So it means that here we have 4 on 7, which is the probability of A prime given B prime. I know that from here one can ask that since 1 minus probability of B is probability of B prime, why can't they just cancel like this and have probability of A prime rather than going through the way we have gone? No, we cannot cancel like that, because this probability of B prime is not depending on any event, but this probability of B prime here is depending on probability of A prime. That is the probability of B prime given that A prime have occurred. But this probability of B prime at this denominator, it is the probability of B prime that depends on no condition, and it can only be obtained from the probability of B that does not also depend on any condition, which is 3 on 10 as we calculated before. Another way to approach this problem is also to use the formula from complementary events. From complementary events, probability of A prime intersection B prime is given by the formula 1 minus probability of A union B, and we know probability of B prime is same like 1 minus probability of B. So we know before that probability of A union B was 3 on 5. So here we have 1 minus 3 on 5 all over 1 minus probability of B, which is 3 on 10. We simplify this, we have 5 minus 3, which is 2 on 5 all over 10 minus 3, which is 7 on 10. If we invert and multiply, we have 2 on 5 times 10 on 7, which is the same thing. 2 times 2 is 4, so it's going to give us 4 on 7, which is the same answer as we obtained before, 4 on 7. So using the two methods, we still give the same answer. And we have to take note that the probability of B prime here, it is not the probability of B prime depending on another event. It is the probability of B prime independent of any other event. So that is why we need to calculate the probability, but from the probability of B that is depending on no event. So all the probabilities on this second trial depends on the probabilities from the first trial, so we cannot use any of them in this place. The probability of B prime on this tree diagram depends on the probability of A prime and the probability of A, so we cannot use it here.